Good afternoon, all of you. Welcome to the fourth TDS webinar of this year, the final one, where it's my pleasure to introduce my colleague and friend Islam Boussaada. So I don't think that Islam needs a long introduction. He's a full professor at IPSA in Paris, and also part of the L2S laboratory of the University, associated with the Université Paris-Saclay. He's been very mobile in his career. So before he has been at the University of Cartago, in Université Paris-Cité, in the Université de Rouen, and now thus at IPSA. So Islam, I know him as someone with a very broad interest: operators theory, dynamical systems, control theory, and of course, with a big specialization on time delay systems. So he has been really one of the main driving forces in our community, witnessed among others by the fact that he was one of the general chairs of the joint IFAC conference last year or this year in Saclay. And on top of this, he was also one of the IPC chairs at the preceding IFAC TDS workshop in Udine. So Islam, we are very glad that you accepted, and we are honored that you accepted to be here for your talk about a partial pole placement for infinite dimensional systems. So you have the word, Islam. We have time for questions after the talk, but of course, for the audience, feel free to post questions or comments in the chat already, which I can also follow up. You have the word, Islam.
So thank you very much, Wim, for the introduction. First of all, I have to thank you, Wim and Gabor, for the kind invitation, as well as for the great job you did for our community. So today I will speak about partial pole placement in the sense of prescribing the exponential decay of solutions, not only for time delay system, but also for some classes of partial differential equation. So my talk will be as follows. I will start with motivations, and I will try to state in more generality the problem I'm considering. I will try to introduce also some special functions, which are the Kummer hypergeometric functions, which are the main ingredient of the partial pole placement. The property behind the partial pole placement, the main one is the multiplicity-induced dominancy. I will try to focus on the single delay case for that time delay systems. I will show several applications and numerical results and software for this prescribed stabilization. And I will present and I will end my talk by extends to multiple delay case, multidimensional systems, and partial differential equations. Also, I will, if I will have time, I will try to introduce the RRID, which is some property which can also lead to partial pole placement. So let me start with this nth order linear time invariant time delay system with single delay. Here y of t belongs to R. The delay tau is some positive constant. And here I define the order of derivative with respect to the instantaneous state by n. And I define small m as the order of derivative of the delayed part of the differential equation. It is well known that if m is greater than n, so in that case we are dealing with advanced equation which admits an infinite number of zero in the right half complex plane. This talk is focused only on retarded and neutral equations. To define solutions for these differential equations, one needs an initial condition which is a function belonging to the Banach space of continuous function from minus tau 0 into R. So the main question is, if some of the parameter of this differential equation are left free, how one can choose them to guarantee some exponential stability. From control theory point of view, if one consider u of t as an input, y of t as output, and the system defined by this nth order ordinary differential equation. So, and one choose a feedback u of t as given here by this expression, and the closed loop system in this case reduces to some ordinary differential equation. However, in general, control system operates in the presence of delay due to the propagation of information from the output to the system. So that's one include here the delay tau, and studying stability and stabilization become a more challenging problem in all generality. So in the standard way made by engineers consists in considering that the delay tau is equal to 0, then design some controller such that the finite dimensional system is stable, and pray that the delay belongs to 0 tau m, where tau m is the delay margin. Even in this case, no information on the solution decay can be obtained. The second option is to consider the delay into the control design. So in this case, we consider the characteristic function corresponding to the closed loop system, which gives a quasi-polynomial defined by P0 and P tau. And here, the problem that one encounters is that one has an infinite number of spectral values, which are the roots of this analytic function delta of S. It is well known that exponential stability means the existence of some positive alpha such that all roots of delta satisfy real of S is less or equal to minus alpha. And I define the abscissa as the supremum of real part of S such that S is a root of delta. So one can find in these standard books all the information about roots, the roots distribution with respect to time delay system. Let me try to present a simple problem which will help to present the objective of the control approach I'm proposing here. So let us consider this finite dimensional system with input delay, where A and B are real valued matrices and tau is the delay. A may be not Hurwitz, and the pair AB is controllable. The objective here is to design reduced complexity controllers in the sense of they are easy to implement by engineers, and also we need to define some tuning strategy allowing to prescribe the exact exponential decay of solutions. So this problem is not new. This problem, for instance, has been considered by Manutius and Olbrodt when they defined the predictor to compensate the delay effects in the closed loop. So indeed, if one consider a predictor in the closed loop and compute the Laplace transform of the corresponding closed loop system, so we obtain here a polynomial as characteristic functions. This means that in theory, this predictor cancel the delay effects on the system solutions. Unfortunately, from the beginning of 2000, work by Angel Wall and co-authors emphasized this simple example. So consider the scalar equation and consider that we have a delay on the input U here, and we design a predictor as suggested by Olborot and Wanisius approach. And we are expecting that we obtain a finite dimensional system, which is a scalar. So we have only one spectral value. But the problem that when one approximates this controller we have here, one obtains this expression. And by this approximation, as we see here, we obtain a spillover phenomena, which means that beyond the spectral value, which is already assigned by the predictor, we have an infinite number of spectral value. Furthermore, some of them are dominating this assigned spectral value. A solution has been proposed by Sabine and Wim to define filter to identify some frequency region where this spectral value, which is at -1, is the dominant spectral value. But this is not the only paradigm offering such prescribed stabilization. In fact, here we have an approach based on optimization, which is due to Edmund Pinney. This work is almost a forgotten book, where there are some nice developments on optimization to get the spectral abscissa of delay systems. Also, some extensions are given by colleagues from Mexico and with joint work with Rifat Sipahi. On beyond of this optimization-based method, I can cite also the algebraic pole placements proposed by Bretet and Loiseau in these three works. In this approach, the idea is to cancel undesired spectral values by other spectral values which are more appropriate. And here we have also the example of continuous pole placement proposed mainly by Wim and Thomas Vihledal, where they propose, where they establish this pole placement based on the property of the continuous distribution of the spectrum with respect to parameter variations. So let me now go to the partial pole placement I'm proposing, and let me recall what is a Kummer hypergeometric function. First of all, I have to define the Pochhammer symbol or the ascending factorial as alpha bracket k, which is inductively defined. Alpha bracket 0 is equal to 1, and alpha k plus 1 is equal alpha plus k, alpha k. What is interesting in these Kummer hypergeometric functions, which are defined for parameters a and b belonging to C, such that b does not belong to Z minus, and a variable z belonging to C. So one can represent the Kummer hypergeometric function as done here. Phi of a, b, z is equal to this series that we have here. So we know that this series converges for any z belonging to C, and the Kummer hypergeometric function satisfies this second order ordinary differential equation, but with respect to the complex variable z, as you see here. What is interesting in these hypergeometric functions is their representation in this integral form. So one can write Kummer hypergeometric function a, b, z as a constant multiplied by integral from 0 to 1. We have an exponential kernel, and we have here a Bernstein polynomial. Bernstein polynomial are written as t power alpha 1 minus t power beta. So one of the results concerning the location of zeros of such Kummer function has been proposed in 41 in this paper by Tsvetkov. Unfortunately, the result of Tsvetkov has some mistakes. So we corrected the location of zeros of hypergeometric functions in this work using 1 century ago work given by Edouard Einar Hill, where we exploited the green Hill transforms to obtain this result. Also notice that the mistake by Tsvetkov has some propagation on other works, like the work 3 that I describe here. To explain in simple terms the partial pole placement. So let me consider, as for the finite pole placement, the scalar equation x dot plus a0 x of t equal u of t, where u of t is just a the delayed state that we have here. The corresponding characteristic function is given by delta, defined by 3. And in this work here, this note of MTNS, we have showed that this quasi-polynomial admits a double root at s equal to s0 if and only if s0 is equal to minus a0 minus 1 over tau, and the control parameter here, a1, has to satisfy this equality here. The most important is that in that case, S0 is the rightmost spectral value. Indeed, you can see here for given values of tau and A0, the dominance of the multiple root at S0, but you can also observe in the right figure that if the delay tau is considered as a delay parameter, so one can choose exactly the decay rate by choosing the appropriate value of the delay. This is the main idea. Now, let me just give some remark here, is that multiple spectral values are not necessarily dominant. In fact, if one revisits the problem of stabilization of a chain of a double integrator, as described in equation 5. So the maximal admissible multiplicity here is 2, which is satisfied if alpha is given by this value and the complex, the double root is given by minus 2 over tau. But in these two works, it has been shown that a necessary and sufficient condition to stabilize a chain of a double integrator is to have here 2 delays. Unfortunately, we have only 1 delay, so that we can prove that there exists some spectral value with positive real part, even we have here a double root. And this problem here is related to the sparsity of the polynomial P0 defining the finite dimensional part of the quasi-polynomial. Let me now go to the general framework for single delay linear time invariant differential equations. So I consider here that m is less or equal to n. By using Laplace transform, we obtain the characteristic function defined by 7. Here, I define the degree of the quasi-polynomial as the sum of the degrees of the involved polynomials plus the number of delays. So one can see here that P0 is of degree n, P tau is of degree m, and we have a single delay. So the degree of this quasi-polynomial is equal to n plus m plus 1. Also notice that the multiplicity of a quasi-polynomial 0 is bounded by such a degree. So one cannot obtain a spectral value with multiplicity greater than n plus m plus 1. Also, I'm speaking about multiplicity-induced dominancy. This property refers to condition in terms of coefficients, the parameters of the quasi-polynomial 7, guaranteeing that a multiple spectral value is the spectral abscissa. So here the methodology is based on 3 steps. First step that I entitle interpolation problem. So we consider the quasi-polynomial delta and we consider some s belonging to R. So the number S0 is the root of multiplicity equal to the degree of the quasi-polynomial if and only if these two relations given by 8 are satisfied. So by taking into account and considering the particular case of an minus 1, one obtains the explicit value of S0 that we have here. So S0 is written as a function of n, m, the delay tau, and the particular coefficient an minus 1. The second step of the methodology is based on the shifting of the spectrum. So to study the shifted quasi-polynomial, let me define the change of variable z equal to tau s minus s0, where s0 is the multiple root of the original quasi-polynomial delta. So the auxiliary quasi-polynomial delta tilde, defined here by tau power n delta applied as s0 plus z over tau, is written as defined here by 10, where by these two equations 11, we can establish the link between coefficient of the auxiliary quasi-polynomial and the original quasi-polynomial, as you see here. So bk as functions of s0 and aj, and beta k are defined as functions of s0, alpha j, and of course the delay tau. So the last step is what I call integral representation. Thanks to this interpolation and this relation between coefficient of the original and the auxiliary quasi-polynomials, one can prove that the auxiliary quasi-polynomial can be written as z power m plus n plus 1 over m factorial. One can see here that when delta admits a root at S0 with multiplicity n plus m plus 1, thanks to this linear change of variable, one has here a root at 0 with multiplicity m plus n plus 1. But the most important is the second factor. As you see here, we have an integral between 0 and 1. We have an exponential kernel, and we have here a Bernstein polynomial. This helps us to say that in this case, the quasi-polynomial is reduced to a polynomial multiplied by some Kummer hypergeometric function. Thanks to the classification of zeros of such Kummer hypergeometric functions, we are able to prove the following result here. So consider the quasi-polynomial delta and let S0 belonging to 7. And here we consider that S0 is a multiple root with multiplicity n plus m plus 1. So in the case of retarded equation, that means when m is less than n, we arrive to prove that S0 is a strictly dominant root of delta. However, in the neutral case, with having a root at S0 with multiplicity n plus m plus 1 allows us to show that all the spectral values are in some vertical line defined by real of S equal to S0. More precisely, the imaginary part of each root satisfy this relation defined here by this set. As I emphasized in this slide that S0 is completely defined by an minus 1, n, m, and tau, so one can observe that this GMID property, which is the property exploiting the maximal multiplicity one root can get, so it is, you can see that you don't have any degree of freedom in assigning the spectral value as 0. That's why we proposed to focus on intermediate multiplicity rather than considering the maximal multiplicity. And here we arrived to show that when one considers a spectral value with multiplicity capital M, which is less or strictly less than the degree and greater or equal to the order plus 1, so the quasi-polynomial delta can be written as represented here. So we have a polynomial in S multiplied by some integral from 0 to 1. We have here the Bernstein polynomial. We have the exponential kernel. However, we have here some additional polynomial P of t. And we showed that this polynomial P of t admits a degree which is equal to n plus m plus 1 minus the multiplicity, so that one can show that delta of S in this case can be written as a linear combination of n plus m plus 2 minus the multiplicity continuous Kummer functions. Unfortunately, the resulting second-order differential equation is extremely involved, and here we have shown the limitation of the Green-Hill transform, which helped us to locate the zeros of the simple Kummer hypergeometric function. We also proposed some alternative to Green-Hill transform to show the dominancy of multiple spectral values. In fact, the dominance of condition are established by contradiction. First of all, one assumes that there exists some spectral value, S1, which has a real part which is greater than S0. Then one extracts only the imaginary part of the integral representation given here. Okay, so we get this equality, where x and omega are just the real part and imaginary part of the spectral value, the potential spectral value S1. If one takes a look here, so T, the Bernstein polynomial does not admit any root in the interval 0, 1. Also, this exponential term does not vanish in the interval 0, 1. So if one finds condition on P of t such that P admits a constant sign between 0 and 1, and one finds the condition on the system parameters such that omega tau is less than pi, so in that case, the sign function does not change sign, P of t does not change sign, Bernstein polynomial is of constant sign, and here we have an exponential term which is positive. So this is this contradiction is proved if we arrive to solve these two problems. Interestingly, one solves this problem by using some algebraic and semi-algebraic equation rather than transcendental equations. In fact, the main idea is as follows. So one assumes that there exists S1 as described before with real part which is greater than S0, and one can write this equality 14 as equivalent to the fact that S1 is a root of delta. Next step consists in truncating this exponential 2x that we have here. So if we arrive to truncate this quantity, we know that this truncation is between the exponential and which is greater or equal to 1 for any positive x. Then we arrive to show that this family of polynomials in both x and omega is always greater than 0 for x greater than S0. And this amounts to study the positive zeros of quadratic polynomial in omega square. Okay, what is interesting here? It is interesting that if one explores, for instance, Fk, the family Fk, and arrives to find condition. So when one analyzes Fk plus 1, so the set of solution increase. This is first property. Second property is stationarity, in the sense that there exists some order n star until which condition cannot change. So we obtain the optimal conditions guaranteeing the dominancy of the multiple spectral value. So to show you the interest in using the MID property in some concrete example, let's consider here the inverted pendulum on cards, and let me consider controllers which are written as Kp theta of t minus tau plus Kd theta dot of t minus tau. And I consider here the model of the inverted pendulum. If one considers the standard design. So by assuming that tau equal to 0, one can design a controller which gives such stabilization clear without any oscillations. However, when one increases the value of the delay, for instance, to 0.13 seconds, one can start to observe some oscillations, as you see here. Now, if one increases this delay to 0.17, we see that we lose stability. Okay. Now, let me consider that the delay is equal to 0.17 seconds, and let me use the MID property, and you see that you arrive to some performance comparable to what is obtained in finite dimensional systems. Let me consider another application. So here, assume that we have a plant, and one would like to design a PID controller able to stabilize the closed loop system solution. So here we have gains Ki, Kp, and Kd, and our objective is to find values of them achieving a prescribed stabilization in closed loop. In fact, if one computes the corresponding transfer function, we obtain the function given by M of S here. If we take a look on the characteristic equation, we see that we have P0 of degree 2 and P tau, which is also of degree 2. So we are dealing with a neutral equation here. And we obtain the following results. So for arbitrary Kp, Ki, Kd, and delay tau, the roots of the closed loop characteristic function are bounded by 4. Furthermore, the quasi-polynomial admits a multiple spectral value at S plus and minus with algebraic multiplicity 4, if and only if the controller gains are defined by this system 19. Also, if one consider these values and consider here S plus rather than S minus, so one can show that S plus is nothing but the rightmost root of the characteristic function. Also, these multiple spectral values are related to some optimization problem. So this problem has been already defined by Edmund Pinney in this book. So consider here, for instance, a second order system, and we are trying to control this system with a proportional derivative delayed controller. So we have gains K0 and K1 to tune. Here, the corresponding quasi-polynomial is defined by P0 plus P1 exponential minus S tau, where P0 is given by this expression, and P1 is equal to K1S plus K0. So the spectral abscissa of 20 is defined by gamma K0, K1, which is equal to the maximum among all complex numbers S belonging to C of real parts of S, such that S is the root of the corresponding quasi-polynomial function. Also, we consider the problem of global minimization of the spectral abscissa of the closed loop system 20. So we define here gamma 0 as the minimum on K0, K1 belonging to R2 of gamma of K0, K1, and let's define delta as the discriminant of the polynomial P0. And we are able to prove the following. So what we can see here is that the global minimization of the spectral abscissa is only achieved at multiple spectral value. In fact, we arrive to show that the spectral abscissa function is quasi-convex. Also, this global minimization holds in the following configurations. So here we identified some critical value on the discriminant of P0, which allows us to characterize precisely which multiplicity will help us to obtain the global minimization. So in the works 1 and 2, we identified this critical value of the discriminant, and we characterized the dominancy of the double, triple, and quadruple spectral values. And in the works 3, we arrived to show that such multiple spectral value are local minimizers for the spectral abscissa. And finally, in the last work that I present here, we arrived to show this theorem and to show that this optimization is global among all the admissible values of K0 and K1. Let me move now to a more concrete application that I learned thanks to the collaboration of colleagues from Budapest. So here I'm revisiting the modeling of the CNS action on the human balance. As you know, there are communication delays from the central nervous system to muscles, and there are also informations going from the muscles to the central nervous system. And we consider that our balance is guaranteed thanks to two types of controller. So the first controller is called the neural controller, and the second controller is some passive controller, which is based on the stiffness and viscosity of the ankle joint muscles. So as emphasized in this first work by Gabor Stepan, modeling the mechanical part of the human balance is already clear and understood from the mechanical point of view, and the only challenge is on how one can model the action of the central nervous system. So in the lab, in the human balancing research group at BME, they have some experiments on balance board with various radius and various size h, as you see here. And the idea is to try to understand the action of the central nervous system on our balance. So colleagues from BME made some approximation of the response time, the necessary time allowing to act from the central nervous system to the muscle. And we arrived to establish with our colleagues this kind of block diagram modeling the action of the CNS. As you see here, this is the neural controller. This is a model for the neuromuscular contraction. Here we have a model of the inverted pendulum, and here we have the passive controller, which is based on the stiffness and viscosity of muscles. We have two delays here. First delay related to time, as emphasized here, tau 1, and here the delay tau 2. So the corresponding closed loop characteristic function is given by this retarded characteristic function characterized by a polynomial P0 of degree 4 and the polynomial P tau of degree 2, as you see here. And here we consider that tau is equal to the sum of the two delays, tau 1 and tau 2. After the identification made from experiments, we consider that the perfect behavior of balance is guaranteed by some values Ka star, Kd star, Kp star, Kg star, and tau star for this polynomial that we have here. And this corresponds to the MID property, since we know with precision, with some precision, the propagation delay and the reaction delay. And we know also the decay, we can approximate the decay so that one can model the perfect behavior by the MID property. Two problems are considered here. The first problem is the impact of increase of delay. So when you are tired and or when you have some with aging, for instance, so the reaction delay will increase. So I consider here that we have nominal value of the delay, and we have here some increase of the delay, communication delay. Also, we investigate the effect of the ankle joint stiffness, which decrease with aging also. So K will be equal to K star minus some epsilon. And the question that I will try to present here, which of these parameters is responsible of oscillations? And this is the answer to this question can be obtained by sensitivity analysis. As emphasized here, in the left, one can see that the delay, when the delay increase, so the multiple spectral value will split, and we obtain here some crossing frequencies at some critical delay tau kit. And for when one perturb the value of the stiffness, so the crossing will be made through zero. So we don't have any crossing frequencies either. So oscillations are the responsibility of increasing the delay of communication. Also, this MID property has been exploited in design of controller to reduce vibrations in mechanical structures. So here we consider the piezo-actuated flexible beam clamped at one edge, as emphasized in this photo here. And so the modeling of this problem is based on some PDEs with nonlinear coupled PDEs with nonlinear boundary conditions. By using finite element modeling, one obtains a linear system, but of huge number of degrees of freedom. Next step consists in considering the dominant modes that one would like to remove from the spectrum of the flexible beam. Here in the Laplace domain, we obtain the transfer function. So we have here two outputs, z of s and y of s, and two inputs, u of s and omega of s. Here we proposed this autoregressive control design, the controller you have here. So C of S is just the ratio of two quasi-polynomials. And one has to tune 4 parameters and eventually to find an appropriate delay to stabilize and to catch these vibrations. In fact, if one forces a root of multiplicity 3, one can obtain this value of S0 when one chooses N0 and R0, D0 and DR0 and the delay tau as given here. And one can see here the effect of this control law. Here in blue, it is the open loop dynamic, and in red, it is the controlled dynamics. Here, it is with respect to the output Y, and this is with respect to output Z. And here you can see the command signal, which goes until minus 120 volts. So here, let me share with you some slides on the dedicated software P3 Delta. So P3 Delta is a software which can help to design based on MID property. Let me revisit here the inverted pendulum on cards. So if one opened the P3 Delta interface, you can find several functionalities, and one has to go to control-oriented MID. In this frame, you have to choose the order of your system, the order of your controller. The software will allows you to complete the model parameters. And the software will compute the controller gains, guaranteeing some prescribed stabilization. So here, the order, you complete your damping, and here, first figure that you obtain is what I call admissibility plot. Admissibility plot is the domain of the validity of the IMID property for intermediate multiplicity inducing dominancy. One can see if one consider a spectral abscissa and prescribed stabilization with spectral abscissa around -1, for instance, here, so we are not able to find an appropriate delay. However, if one would like to assign the spectral abscissa at -6, so we make a projection on this curve here, and one can identify the value of the delay, guaranteeing such a decay. Also, one can obtain the explicit values of the controller gains. As you can see here, you have the gains B0 and B1, and you have the appropriate value for tau to design such multiple spectral value. Next, if there are some uncertainties on the delay, one can plot this sensitivity representation showing the splitting of the multiple spectral value. And at last step, one can represent the time response of the closed loop system solution. As you see here, you have a perfect decay. And here next, one can print all graphics obtained from the software. So this software has been made with undergraduate students from my engineering school, IPSA. So let me come back to here to extensions of this partial pole placement. First extension corresponds to the case of scalar equation with two delays. And we have in this paper, we obtained this result showing the dominancy of the triple spectral value that we can obtain by tuning A1, A2, as described in 25. And we arrived to show that the GMID holds in this case. Some extensions also has been made for planar systems in the perspective of generalizing this property to multidimensional systems. So without any loss of generality, one can consider the planar system 26, for which the corresponding characteristic function can be obtained by computing 27. And here, let me go to the generic setting. So in the case of planar systems, one obtain characteristic functions which are written as polynomial P0 of degree 2, as described here, P1 of degree 1, and P2 of degree 0. And here we assume that A11 is different from 0, and A20 is different from 0 to still in some generic setting. That means the quasi-polynomial delta is of degree 5, as one can make the sum 2 plus 1 plus 0 plus 2 delays. So in these two works, we considered first the GMID property based on the principal argument under the refinement of Gabor-Stepan. We obtain the dominancy of the spectral value of multiplicity 5 for the quasi-polynomial delta 5, when the coefficient A0, 0, and all the remaining coefficients satisfy this equality 30. We show that S0 is a strictly dominant root of delta 5 when S0 is defined as described in 30 here. And if this coefficient minus A01 is less than 5 over sigma, then the solution of the corresponding planar system is exponentially stable with the decay S0. So this condition here guarantees that S0 is negative. In the case of IMID, one has to introduce this Lambert omega function, and we consider this condition on the parameters of the planar system. So I consider kappa plus as the principal analytic branch of the Lambert function, and kappa minus as the second real branch of the omega Lambert function. And we have the following. So for arbitrary delay tau, the quasi-polynomial admits spectral value with multiplicity 4 if and only if S is equal to S plus or S equal to S minus. And to obtain these spectral values, the system parameter has to satisfy this equation star plus or minus. Furthermore, if S plus or minus is negative, if and only if, we have these three conditions. If one arrive to find condition satisfying one of these three conditions, so you have the negativity of the multiple spectral value. Lastly, if one change the parameterization of the system by defining mu as 2 kappa plus or minus plus 1, so if we consider equality star plus, then there exists some u star greater than 0, such that S equal to S plus represents the spectral abscissa for all mu belonging to this interval. In some sense, we are obtaining here conditions on the multiple spectral value to be dominant for this planar system. As an application, we can consider here the linearized inverted pendulum, and we consider a strictly delayed controller given by 35 here. And one can use the previous results to find the spectral abscissa as well as the control parameters. So you see here that the spectral abscissa is a function of the delay. And if you, for instance, if you want to set your decay at -2, so you have just to fix your delay to 1/2, as can be computed here. And we see here the spectrum distribution corresponding to the closed loop system. Also, one obtained some extensions in the control of some partial differential equations. For instance, let us consider the transport equation described here. And let us consider the PI boundary control for such a transport equation. So using MID property, one can force a triple spectral value for delta, which corresponds to a neutral delay differential equation by setting S0 equal to minus tau, Kp and Kd as described here. One can see the nice decay that we obtain on solutions of the transport equation. Also, for extensions, we arrive to show that multiple spectral values are not necessary to assign the decay of the closed loop system solution. In fact, we introduced another property called coexistent real roots inducing dominancy, which allows us to show the dominancy when one makes a saturation of the number of roots corresponding to the degree of the quasi-polynomial. We have, for instance, here the G for generic CRID property, And we have here intermediate property CRRID. Okay, so to show the dominancy, in the first case, there are no any condition, so that by setting 3 roots, by interpolating 3 roots for the quasi-polynomial, you are sure that S1 is the dominant. However, in the intermediate case, so you don't have the number of roots is not equal to the degree, so you have additional conditions to check here. So as we consider an example for the transport equation, we see that S1 is always greater than S0. This means that the GMID property gives faster decay than the CRRD property. However, if one considers robustness information, so one can compare the GMID property with the GCRD property and show that the delay margin guaranteed by the second is better than the one provided by the GMID property. So one can say that the GMID gives better performance, but the second one gives less sensitive design. We revisited also the autoregressive control, autoregressive boundary control of the transport equation, recovering a quasi-polynomial which is given here, which is called Hale quasi-polynomial. The interest in this quasi-polynomial that 2 delays appears. So the first delay is the propagation delay coming from the transport equation, and the second delay, tau1, is related to the control law we are considering. So that the quasi-polynomial exhibits the first delay, the second delay, but also the sum of these 2 delays. And in that case, we obtain the following conditions. So if the delay tau1 is some multiple of the delay tau2, which is the propagation delay, so one can force multiplicity to assign the decay. Here, if k is equal to 1, so one will look for double spectral values, and if k is greater than 1, so one can look for triple spectral values guaranteeing the validity of the MID property. However, if the delay tau1 is not a multiple of the delay tau2, we are able to estimate the vertical strip in which all the spectral values are located. So by defining this row hat of tau as follow, and we obtain this graphic method allowing to choose a point in this yellow region, guaranteeing the decay for the system solution. Fortunately, both autoregressive boundary control and pointwise control of the wave equation involve the Hale quasi-polynomial, so that in these 2 papers, we exploited properties of Hale quasi-polynomials to stabilize on midpoint prescribed stabilization and on boundary control of the wave equation. Finally, to revisit the last type of the control, which is the internal control, let me visit here the wave equation with the controller capital U of xt that you have here. And this controller is nothing but an instantaneous plus a delayed damping. Okay, so we have this first result. A complex number is a spectral value for the problem P if and only if it is a root of the quasi-polynomial delta 4 of lambda uniformly with respect to n. As you see here, we have an infinite number of quasi-polynomials. So 2 options are proposed to control the dynamics of solution of the problem P. The first option is to consider initial conditions which are characterizing some precise quasi-polynomial indexed by n. So if you consider condition U0 and U1 given by these two expressions, you are able to assign a global optimum exponential decay for the problem P. If you choose beta, as described here, and alpha star as the permanent real root of the polynomial Q of lambda given here. It is a third order polynomial which has a permanent real root. So this root will be the value for this alpha star. So the second option is to harness the delay and dependent stability. In fact, in this work by Niquez and Pignotti, it has been shown that if one consider that alpha is greater than beta, then the solution of the closed loop wave equation are exponentially stable, which means that uniformly with respect to n. And the added value here is that we consider any initial condition belonging to H1 0 0L times L2 0L. And here we choose alpha star greater than beta to guarantee that we have a delay and dependent stability. But by this choice of alpha star and beta, we are able to assign the exponential decay for the nth mode decay with respect to the characteristic function. And here you see the open loop dynamic and the closed loop dynamic with internal control for n equal to 3 and alpha equal to 0. And here we have the delay value and the other gain value. So to conclude this talk, I presented today a new prescribed stabilization paradigm based on Kummer hypergeometric functions. So the ensuing strategy is easy to implement because we are using a simple controller structure and which is robust with respect to uncertain parameters. So in this work that I emphasize here, we have a description of the mechanism, coalescence, and splitting of multiple spectral values of time delay systems. So a wide range of applications have benefited from the partial pole placement, and dedicated software, which is called P3 Delta, has been developed. New versions also are in progress. What's still to do? So it appears that the prescribed stabilization extends beyond the CISO and the single delay case, as you have seen. The planar systems and the two delay case benefit from the MID property. Also, only a few results on the CRID property, which needs further efforts and attention, and further extension to the control of other classes of PDEs are in progress. So I have to thank all my collaborators and colleagues for inspiring discussion. I thank also CNRS Africa Joint Research Program, which is granting my research for 24-28, and a grant from Ashcode University Paris-Saclay from 23-25. Thank you for your attention.
Thank you very much, Issam, for this very nice talk. It's much appreciated.